So I'm Ian Wetherbee, and we have Jay with me as well. So we sort of jointly run everything to do with patents at Google. So I run all of the external patent search, patents.google.com, and the public data sets. And Jay's team runs all the internal sort of patent analytics, data science for Google's portfolio. So jointly, we know a lot about patents and a lot about using a whole lot of patent data for either public analysis, public distribution, or sort of private data mining analysis. So along the way, we picked up several Google tools and sort of Google ways of dealing with this amount of data to very quickly build models and very quickly derive answers. So hopefully we're going to share some of these tools with you, and yeah, those are the tools that are easily accessible to the public. So we're going to run through what data exists and then some example notebooks and analysis that exists inside of Kaggle. And Kaggle is just a Python hosted notebook environment that makes it really easy to query data in BigQuery without a whole lot of setup of accounts. And then we'd love to talk about future research that we're working on and have maybe more of a discussion about data sets that obviously are probably missing, or types of data analysis that may or may not be good for this type of BigQuery ecosystem. And then we'll leave you with some links, of course, to get started, maybe on your own time, additional reading and things. So as I said, I run Google Patents, and our mission is to make patent information universally accessible and useful. So we had done this for many years in just normal Google patent search. And somewhere around 2016, 2017, we started trying to help some academics run some sort of big data calculations over the entire patent corpus. So we're talking a couple terabytes worth of data, but potentially lots of analysis of the hundreds of millions of citations that are made between the different patents. And there's a very small Venn diagram overlap of IP professors and people who know enough about computers to write a bunch of complicated scripts and to be able to load and maintain a database of that size. So we started looking at what we could do to make the patent data more accessible and useful for sort of bulk analysis and research. And we landed on the Google Patents public datasets effort to make it much easier to query large amounts of patent data. So this was the sort of traditional problem in research that we were trying to tackle. You have data coming from many different sources. You usually don't have just a single nice clean table. Usually you're trying to analyze multiple tables together. For instance, patent metadata, you've got examiner actions, and you've got some information on public litigations. The first step for all these actions is always get it all normalized, get it all cleaned up, get it in a single database so you can actually execute your queries and analyze potential links between the different variables. So this was a lot of effort, sort of computer science or data movement effort that needs to be done by every user before they could even start asking the question and figure out if there's anything there. So this led us to the conclusion that raw data, the data you might find on, say, Harvard Dataverse or any of the other sort of bulk CSV download sites, it's still quite a ways away from being usable. So you get it as a CSV, but you have to go through all these different steps before you can analyze it. And every single user that downloads that raw CSV has to go through the same steps before they can analyze it. Specifically linking up the number formats to make sure they match, loading the data and updating the data if it starts getting updated quarterly because of new patent publications or cleaned up data sets. And we hope that every user can do this type of loading and linking and managing the same way, the correct way, so that they all come to the same answer. But that's not necessarily a given. So we can gain a lot of efficiency, but also things like reproducibility if this loading and linking and updating is happening by a single source, and everybody else can come in at the analyze step. So all of this effort is done by just one team or one person that maintains the data set in the most efficient and usable format as possible. This wasn't necessarily possible with something just like a CSV file, but around that time, there was a bunch of cloud products that were coming out. You had Amazon, you had Microsoft, you had Google coming out with sort of cloud database products. And Google being Google, we took a look at our own cloud database product, which was BigQuery. And we said, this has some cool properties in terms of payment, in terms of sharing data, in terms of just sort of silos that you don't really get with the other products. And we'll get to that in just a sec. But it made this type of a solution potentially, very attractive for the research workflow and for collaboration. So yes, Google BigQuery. So in BigQuery, as opposed to a traditional sort of relational database that lives on your laptop or lives on some server in your university, the entire database, there's only one instance of it per country, let's say. So anybody who submits data to and stores data in the, say, US BigQuery instance, as long as the data is shared with the right access permissions, anybody else can join tables together in the US BigQuery instance. So there's no longer sort of every university has their own SQL database shard. Any data in the system can be immediately joined together with a single SQL query and immediately analyzed, as opposed to having to download one set first and upload it into your own database. So that's assuming that everything lives in BigQuery. And we have quite a sort of bootstrap collection of data sets that we put together, but we'd love to have more add to this system, as every additional data set that lands in there enables questions across all of the joins to all of the previous data sets that are already in BigQuery. So for instance, say Patents View is working on maybe gender, inventor gender, trying to link that to any of the existing data sets on, we have all the PEDS data, all the examination records, we have all the patent data filings, say number of inventors that exist, PTAB cases, we've got Kemble data. So linking all of these different data sets that already exist in BigQuery with this one new table that you can add as a researcher. And that one table could start out as entirely private. So only you as a researcher in your group and maybe your collaborators, you can share it with them. Only they have access to this one new in progress research table. But you can join that private table with all of the public data that's sitting there. And potentially with maybe another researcher that has another in progress semi-private data set that might need permission to access. So this has sort of dramatically transformed inside of Google how we've done our own research. So you can think about linking some private data sets that Google might have to the public world of patent data to easily fetch metadata, dates, citations, PTAB cases, any of this other metadata. So I mentioned a couple of data sets that we had. Here's a more thorough list, but there's still data sets that are growing beyond this and data sets from other sources that we haven't linked up here. So the core is this Google Patents public data, and that sort of contains the core metadata of all worldwide patent publications. So this is 130 million rows, one per patent publication, and it has things like, it's got all the different dates, it's got the classification codes, inventors, assignees, citations, and a couple other bits of information. And then it's got title, abstract, and full text for the US patents, and title and abstract for everything else worldwide. The Google Patents research data, this is the table of our quote unquote derived unofficial data. So these are fields that we as Google, we calculate for Google Patents or for our own research purposes, and we publish them. So for every patent publication, we have things like, say, extracted key terms from the full text of the patent, the title and abstract translated to English for all the worldwide patents, embeddings, so more neural network representations of the full text of each patent document. We plan to extend this over time with more and more signals that might be useful to reuse based on some of our calculations in some of your research. We have many, many data sets from the Office of the Chief Economist. Thank you, Andy. So we have many of them, some of them are missing. We'd like to obviously fill out the rest of those. But litigation, the cancer moonshot data, the PEDS data, the PADX, examination research, many sources of data from the USPTO, and of course the patents view data, which is itself a fully fledged collection of patent documents from the US with many interesting derived fields, such as we've gotten a lot of use out of the government interest statements. So patents have these statements if it was funded partially or fully by government, and they've gone through and they've normalized all of these different ways to say a particular government entity. So that data is now joinable with any of this other data here to study things like, say, FDA Orange Book drugs based on government funding. There's data on the cooperative patent classification, the CPC scheme. There's ITC cases. There's Kemble and SureKemble, which are the links between patents and chemistry that exists inside of the patents. And we as Google, we've actually just released our own sort of version of SureKemble. So we've gone through and we've annotated all of the patents for instances of chemistry, so chemical compounds. So if it exists in the text, if it exists in the image, or exists as an attachment file, we now have a single table with billions of rows of patent number, machine readable chemistry that exists in that patent. So this data can be joined up with scientific data such as PubChem. PubChem data exists inside of BigQuery as well. So there's many different links that we can start to build between these different data sets once they're in the system. And all of these data sets that we put in there, we've normalized the patent number, the publication number, to be the same exact scheme. So they all map to the DocDB format publication number. And we have some APIs that are freely available to map any publication number, if it's messy, if it's missing a kind code, to map that number into the official sort of DocDB format so that it joins up with all these other data sets. As I was saying, this is our core data set, the Google Patents public data set. When you're in BigQuery, you'll see it as patents public data.patents.publications. This is sort of the core data set that you'll be working with. This is updated quarterly. So we do regularly update and we snapshot every past quarter. So when you're in there, you'll see every quarter or so, there'll be a dated table that has the exact version of all 130 million patents as they existed in that quarter. So that way you can always do your research against one of these data tables and it would be reproducible. The reason we can do that is storage on BigQuery is much, much cheaper than storage in your local database server, because the storage and the compute power to actually process that data, they live on separate machines, which means they can scale separately. Whereas when you have your local database server, you need to give it dedicated CPU, dedicated memory, dedicated disk. and all of that sort of tied together. You can't necessarily have a petabyte worth of storage attached to, say, 16 CPUs. But in something like BigQuery, you might have a petabyte worth of storage that you barely ever query. And when you do query it, it only uses a small amount of CPU power for the time that it's actually doing the query. So the billing model there is quite interesting and allows for lots of raw data storage for a very cheap price. The other benefit is you as a sort of data hoster, you do not pay for how much people query your data. So the data hoster only pays for the data storage of their table. They don't pay for, say, 1,000 users worth of usage. They don't have to provision a certain size worth of server to handle the traffic. You only pay for the storage. And it's 2 cents per gigabyte per month. So we pay, tens of dollars to host some of our data sets. And then the users that go and query the data, every query they do, it's billed back to that individual user based on how much they query. So it's a nice model to be able to, the people that use the data, they pay for how much compute they use on the data. And the people that might be publishing very large data sets that might get a lot of traffic, they don't have to sort of absorb the burden of all of this usage.
Ian, just real quickly, there was a question from Matt Marks about basically what's the update schedule for full text data on Patents View versus Google Patents. The USPTO has weekly updates. I think I heard you say quarterly, but not sure for what databases that applies.
So quarterly is for our full text, sort of the core data sets. So for this one, the Google Patents public data. Some of the other data sets that we put in there, we update daily or weekly. But for this core patent data, this is actually generously provided by our patent data vendor. So this is actually a snapshot of a commercial database that powers many of the public sort of commercial search tools. So they were generous enough to let us snapshot part of their database on a quarterly basis. So we can't update this database any more than quarterly. But yes, Patents View, I think, has updated their update schedule. And we're actually talking with Patents View to potentially update our update schedule in BigQuery of that Patents View data. Right now, it's a manual process. Sorry.
Ian, can I ask a question, please?
Yeah, sure.
If I decide to upload a data set, do I see statistics about how many people are using or even who's using my data?
Good question. Yes. So you cannot see like the queries that they're doing, and you can't see who's doing it, I believe, but you can see sort of number of queries that use your tables, which is different than, and maybe better than, something like a, Dataverse, where somebody downloads your file once and you don't know if that's being used many, many times or it's being used just once.
And is there anything about like citations to data? How does it work? Because as researchers, we want to make sure that people that use our data also cite it. So is there anything you added to control it for that?
So we did add on the BigQuery pages, there's spots for descriptions. So for each of the data sets, we've added the terms of use in the citation and the paper it came from. But there's no sort of, same as Dataverse, there's no further enforcement beyond here's the citation, please cite this data set. And a lot of these data sets are sort of mirrors of data published elsewhere. So some of these might exist in their official format on Dataverse or somewhere else. And then we create a mirror of the data into this more useful format. So the data doesn't have to live either or. And we're thinking about, that might be something that we discuss, how to maybe make it much easier to import data that lives officially in some other publishing platform. Because with Dataverse, you get a DOI, you get citable data, and people sort of know how to link there. Linking directly to BigQuery is probably not the best thing to do for your maybe official dump of the data. But BigQuery is very useful for actually using the data. So some way to have your official snapshot that gets the automatic DOI, but also linking to the useful version in BigQuery.
So Ian, can I ask a question also?
Sure.
So in BigQuery, you've put all of these different data sets in there, which is super useful. But how do people learn about the different data sets, right? Isn't it kind of caveat emptor, whatever you're using there, right? You never do any quality, or do you do any quality control of whatever you upload to BigQuery? And
yeah, so we do obviously check that the data sets that we mirror are mirrored correctly. So we are not the source of barely any of these data sets. Most of them are mirrors of official sources. So we don't quality check beyond just making sure that they're mirrored correctly. So for our core patent data tables like this one, well, these form the basis of Google patents, and they come from sort of the vendor who gets it from the official patent offices. So we have sort of standard checks, but anybody who's worked with patent data knows that each database, each country has years that are weird. There are problems with US citation data. For some older patents only had some number of US citations. There's various issues that happen just in the core databases, even DocDB. So this database is based partly on DocDB and partly on data that comes from official patent office streams directly. So
great, thank you.
The good part is, the data is much more accessible to be able to quickly ask these questions, as opposed to, here's a 500 gigabyte zip file. You need to first load it into your own database and do your own quality checks before you can even decide to use it. Now it's ready to go. You can pull individual records. You can do aggregations across the whole database in seconds. We didn't even talk about speed yet, but BigQuery makes doing queries extremely quick compared to what you could do on your desktop. So we can do giant group bys, giant joins of all citations to all CPCs of all the citations for 130 million patents, and then count up all the results in a minute, which would take hours or days on your desktop.
One other quick question, if I may. I don't want to throw the timing off on things, but if you were to run a program where you wanted to read the text and you wanted to calculate certain embeddings, can you do all of that on BigQuery, kind of like an Amazon Web Services, right? You can do distributed calculations running your Python program. Can you do all that on BigQuery as well?
So BigQuery forms a nice input source to one of the other Google tools, which is Dataflow. So you can't run Python right in BigQuery. You can run custom JavaScript. So we often write little custom JavaScript functions to do certain calculations that are very difficult to do purely in SQL. So there's an example where we calculate the time lag between, say, like, I don't know, what was it? Between like an abandon and then the final grant or something, or between the filing and the first action, say, using the examination data. So we have this array per patent. We have an array of all the different actions and their dates. So trying to calculate that in SQL might be quite difficult, but we can pass that entire array of, abandoned on this date, filed on this date, granted on this date, all the different office actions to just a JavaScript function. And that JavaScript function can very easily loop over those values and keep track of the first date and the filing date, and then output the final, time lag. And then we can take that output and we can group by it back in SQL land. So it does make it easy to do certain things that might be quite complicated, but it cannot run something like a Python embedding. But BigQuery can be used as an input to data flow, which makes it very easy to run custom Python or any other well-supported language, Java, over BigQuery input rows. All right, so here's just the schema of that core table. I won't run through it too much, but it's got all the numbers that you might want. And then the claims and description, yeah, that's only for US publications, but title and abstract for worldwide. They do also have their original language and the English version. You've got priority claims, inventors, assignees. You have the harmonized inventors and assignees. Those come from the EPO. So they actually have a big table that they map. If the assignees may be misspelled or it's in a different language, they'll map to their version of the harmonized assignee. And this is what appears in PatStat and DocDB. They have a couple different versions of the assignee. It's got the classification codes. So we have USPC, IPC, CPC, FI and FTerm from Japan. And then it's got all the citations, if it's an NPL citation or it's a patent citation. And then for USPTO, there's entity status and the art unit, if it's large or small or micro. Yeah. In the research table I mentioned earlier, we have top terms, similar embeddings. We've pre-computed based on these similarity embeddings, the nearest neighbors from the whole 130 million database. So we've done the big N by N similarity between all the patents to all the other patents to find the ones that are the closest in the embedding space. And we've given those patent numbers that are the closest right in this table. We've also given the raw embedding if you want to use that as an input to machine learning or do your own similarity search. The CPC tree, we've just unrolled the CPC tree based on the CPC scheme, so you can easily query at different levels of granularity. Translated title abstract worldwide, and some information mapped over from an EPO table about the country names and the type of publication based on the kind code and the format of the number and the filing date. So these are more helpful just to debug certain application types or publication types that you see and you're not quite sure what that publication code means. Okay, so what can you actually do with it? Here's an example. This is joining some database on litigation that comes from Unified Patents. So Unified Patents actually maintains a federal litigation database, both federal litigation and PTAB cases in BigQuery. It's not publicly accessible to everybody, but if you ask them, they'll give access for researchers. So you can join this directly with this core patent publications table. They update their table weekly probably, and then this one's updated, our core table is updated quarterly. So you can get pretty good information on even the latest court cases. And then we join it with the classification codes and we figure out sort of which classification codes have the most litigation and who are the most, the assignees that are litigating their patents inside of that particular classification code. So an interesting join there to show fetching data from different sources very quickly without any sort of downloads needed. This is one, this one we did write a small JavaScript function for. We went through by year and we aggregated up based on certain classification code, or not classification, certain examination office action codes, what are common sort of paths through an office action sequence before either a grant or an abandon. So there's many different office action codes, so we just had a list to track sequences of, say, non-final, final, RCE, non-final, final, or non-final, final, RCE, non-final, abandon. And you can see over time how these the number of patents applications that went through this exact path through the office, how they change over time. So there's an example that took a couple minutes to run, but actually processed many millions worth of applications, and each application has tens of these different codes, actions that happened. And here's one that joins the patents view government interest statement on each patent to the assignee of the patent to the actual FDA Orange Book approval for that patent, and what the drug was and what target that drug actually acts on is. So you can see interesting links between certain universities and certain applicants at the FDA, the commercial entity. And then you can see which government organization funded that type of work. So this is joining to the Kaggle table. So Kaggle is a fantastic resource of a whole bunch of chemistry data. It's got the Orange Book in it. It's got all of the compounds and all of their activities against drugs, all the properties of the compounds. Anything you want to do with chemistry, Kaggle's got your data. And now we have some examples to run through in Kaggle. So Kaggle, maybe Jay can introduce Kaggle and tell us why it's so great.
Sure, yeah, and then also just real quickly, Andy, your question about potentially adding new variables like CPC novelty or other metrics, absolutely. So we do have a table that Ian mentioned that has some pre-computed metrics, but this is stuff that if it'd be it's two things. One is we'd be happy to build this ourselves. Of course, we would need to kind of sync with you on how you wanted to define it and get whatever kind of code snippets. But that's stuff that we couldn't host, but that's also stuff that you all could host as well. So basically have a script, you can schedule it, you can generate the output into a new table and make that table publicly accessible. So it's pretty straightforward to do things like that. And yeah, maybe we can follow up as well. And I'd love to hear other ideas or other fields that would be useful for you and or others to be able to calculate sort of en masse. Let me
Thank you.
Start sharing my screen here. Okay. Should be able to see this. Let me see if I can jump between. Okay, cool. This is great. Yeah. Thanks, Ian. So actually, we're gonna execute the code in Kaggle, but just wanted to show folks the other ways that we generally access and interact with BigQuery. One is just the actual kind of BigQuery UI itself. So this is what it looks like, and it maybe looks a little daunting right now, but it's pretty straightforward. You basically have this window where you write queries, you run queries. And then what's nice too here is you can basically see, and this is what Ian was showing, but you can see the schemas. And so like this is our Google Patents research schema. We have the patent publication table, and this is all public, right? This is all under the broader patent public data schema. And then if you just double click on any of these tables, you get to see more. You get to see more. You get to see more, advanced information about these tables, which can help you write queries and kind of navigate them. And then so you can basically see the data types, whether they're nullable, and then some description. You can also see a quick preview, which can be pretty nice. And then additional details: how big is the table, number of rows, that kind of stuff. So often, I'll have basically a query window up, and then have these schemas up, and it just helps you write queries more effectively. The other thing that's nice here is before you run a query in this sort of BigQuery UI, it'll tell you how big the query is. And I actually can't tell. Let me just try to move some. Yeah, here we go. it will, let's see if I had a query up. Yeah, so something like this, like it'll tell you up in the top right corner how much compute you're actually going to use. It'll say like 10 gigs or in some instances 100 gigs. So that can help you get a sense of how much compute you're using, which is a nice feature here. The other kind of, I would say our most common interface that we use internally are Colab notebooks. These are going to be just like your kind of Jupyter notebooks or an IPython notebook, just a pretty standard Python notebook. Really nice to do kind of machine learning, to do additional models. The reason why we don't generally use this for these demos is you can see this kind of chunk in 21, 22, 23 is you have to have a GCP account set up in order to query these tables. And so again, it's pretty straightforward, and I would encourage folks to do it if you're doing this type of research commonly. But it is one more step that you don't have to do in Kaggle notebooks. So that gets us then to Kaggle notebooks. The benefit here, and if you look at the presentation that I believe was circulated to everybody, this link actually works for everybody, and you can literally just click in the link. In the top right corner, then you're going to want to click, well, this blue thing will basically say copy and create new version. You do that, and then you can run it. It's free. You don't have to enter any information, and it uses, if you see this part here, it uses Kaggle's public dataset BigQuery integration, so you don't have to basically set up a GCP account in order to start running these queries. So it's super, super nice for people to get up and running very quickly, and it's also powerful. I mean, you can do basically anything in these notebooks that you can do in a Colab notebook as well. So this is the interface I'm going to use to walk through some of the example queries. Let me stop there and see if anyone has any questions now. I don't, it's tough to see the window with this many screens open, but okay. So let's, first kind of standard, we're going to import some libraries. We're going to instantiate our BigQuery client, and that's it. So now we are up and running, and we can actually be querying all the data that we've been walking through live. So let me just walk through a few examples here. I think basically for folks who know SQL, this will look very straightforward. For folks who don't, what we're basically saying here is these are the fields, publication number, country code, publication date, that we want to pull from this table, and basically how many rows do we want to generate. Now you could set there, right now it's going to be 5. You could set this to 5 million, and it's all very quick. So you basically hit run. Again, that's how long it took. And again, this is querying across hundreds of, or I think it's over 100 million rows of data in this specific table. And then we can just take a look at what this looks like. So now this should look very familiar to folks. This is basically, your standard data frame, your standard CSV, your standard table that, is the general framework for most research models. Couple things to highlight here. Some of the fields are very nice and easy, like, publication number looks very natural. Publication dates, right? This is actually in an integer format. So you have to do a little bit of manipulation to convert this to a date, which I'll show in a second. And then these fields, or a bunch of these fields, are actually nested fields. So some of these cases have multiple inventors, multiple signees, multiple CPCs, multiple citations. And it can be a little bit tricky to basically pull those out and to flatten them. And so we have a query that shows you here basically how to unnest and flatten these. And so what we mean by unnest here is, imagine like this patent is citing, let's say 3 patents. Right now, all 3 of those citations are stuck into an array in this field. And what we're doing by unnesting is essentially adding a new row for each citation, so that instead of this 005 patent appearing 1 time, it would appear 3 times, 1 for each citation. So that's what this cell gives an example of. And then you can see here is, again, the 8 million patent now is listed multiple times for each of its CPCs for each of its citations. So it's basically just a way to flatten up those nested fields. Okay, so now how do we jump from this to doing more advanced analytics? So here's an example where basically wanted to show how quick it is to use this interface to pull some data and actually build a model and run it. So what we're doing here is we are basically, this is 2 queries then sort of union together. We're going to pull in 1,000 patents where the assignee has university in the name. So these are basically university patents, and 1,000 where it does not have university in the name. And we're going to generate some summary statistics. So we're going to actually pull in all of the claims in these patents, and we're going to very quickly calculate how many words are in the claim. So again, this is not like, this is not something we're going to publish, but just to show how you can generate these types of metrics very quickly. So we're going to say how long are the claims, how many inventors are there, and then this is what I was alluding to with those date fields. You have to do a little bit of massaging because they're integers. So we're going to cast the integers to a string. We're going to then cast those to a date field, and we're going to see how long the case was pending. So filing date to grant date. Okay, so let's run that. Again, this one takes a touch longer because this claims is actually it's a lot of information, or it's basically the full claim text for every patent. This is our data frame now. It's just again called DF. And we'll take a look at the first 3 rows and last 3 rows. You can see here, right, these are university assets. And then these are the metrics. So how many words were in the claim, how many inventors, how long was it pending, and then how many backward citations. So just a toy example, but illustrative. And then, yeah, so then you can basically just, we're gonna create our X matrix or X data frame with some independent variables. So claim length, number of inventors, pendency, and citation. And then we're going to try to basically see how well we can predict, or try to build a model that can differentiate between university filed patents and non-university filed. So generate those 2 data frames. Again, that's very quick. We're just going to train a very basic logistic regression and then show the, sorry, I forgot to run that. And show the summary statistics. So that's it. So I mean, you're right. You can go from querying 100 million rows of data, summing up the number of words in each, or in the claims, and running a logistic regression, and that takes like under a minute to run. So super powerful. Okay. Some of the even more sophisticated work here is, this is what Ian mentioned in one of the research tables, where we've pre-computed things like unique text, top terms, and embeddings. And so you can do all sorts of things with that data as well. So let's pull that in. Let's not show the whole thing. Okay, so, I guess it's only, yeah, sorry, that's only one for now. But you can see we pulled in the abstract, the claim, the top terms, and then this is the embedding that we've pre-computed for every asset. So you can very quickly pull that in. And with that, you can do things like calculate the similarity between patents very quickly. So now we're going to be generating the embeddings for 100 random patents. And basically this is all it is, or this is the crudest way that you can do that, is we're going to sort of put the embeddings into a list, and then we're just going to do a pairwise cosine similarity amongst the embeddings. And now you have a very straightforward sort of matrix that suggests the similarity between these assets. So if we were to blow this out, it'd be 100 by 100. And then you can do more advanced things, like you can build a clustering model. So basically an unsupervised clustering where the input is those embeddings, and you can cluster assets. And so this is basically how quick that is. So now we're kind of getting a little redundant, but I think we're just trying to illustrate how quickly it is to read in massive amounts of data, run some general statistics, and then actually build some models. You can build a CPC classifier with the embeddings. So this is basically, we're randomly sampling 10,000 patents. We're pulling in the embeddings. We're building a multivariate model where, based on the top level CPC classes, and then basically leveraging TensorFlow and Keras here. And then, this is what the output looks like. For each asset, then it's the prediction of the likelihood that this asset belongs to each of the 9 top level CPC codes. And then you can also do raw text. So this is basically actually just pulling in the raw text of the abstract. So instead of the embeddings, the abstract, and you can do the same thing. Now this cell, we ran into an issue this morning. I think there's a different TensorFlow version here. So if folks want to do this, let us know, and we can get you this update as well. But overall, just want to show like a lot of powerful stuff you can do very quickly, essentially for free in Kaggle using BigQuery. And then we have in the back to the deck at the end, we have some links to some other code that we've open sourced, and basically this all lives on our Patent Public Data GitHub account, where more advanced machine learning models, but all kind of in this framework, a sort of Colab notebook that reads on BigQuery and then does some machine learning, but all in the cloud and fast and effectively. So let me stop there and see if folks had any questions about any of that. Questions, comments, things to dig back into.
A small question, Jay. Can researchers download the data from after they merge the datasets to work on their own machines?
Yeah, sorry, I'm glad you raised that. I skipped over that. You can. There's a couple ways to do that. One is, and the couple ways kind of depend on how much data you're trying to export. In this UI, there's an export option where basically you run a query. Let me actually see. Sorry, I can't. Let me just try to show that here. All right, so if you see here, you can click this Explore Data. This Explore with Sheets will essentially export to a sheet, and you can explore with Data Studio, which is a Google tool as well, or you can do this Save Results, and this will basically let you download it or save it in these different file formats. There are size limitations here, so you just save up to a gig to Google Drive, or the CSV, or you're capped at 16,000 rows. So in some instances that might be enough, in some instances that might not be enough. A gig is pretty good size. The other thing you can do is in Kaggle or a Colab notebook is you can basically execute the query to a data frame, and then you write .csv, that data frame, into your local machine, and that I believe you can get around some of the row limit restrictions that way. So those are kind of the two flavors. I think there are ways too where you can get around any of the limits, but you may have to set up like more sort of advanced GCP storage accounts.
Yeah, you can export, if it's larger than a gig, you can export it. Yeah, you can get it from the data frame just locally. Or you can export it directly to cloud storage. So you can export the whole 2 terabyte table to cloud storage. But that means that you need to have a GCP account set up to sort of hold that exported data until you can download it.
Guys, I have another question, more about the data itself or for the US patents. I asked it earlier in the chat. Specifically before the 1976, do you guys have any sense of how complete the data is for the US patents, and whether and when does the data on that contains inventor names, assignee names, and their location, when does that start?
All good questions. I don't know the exact answer off the top of my head. I know Google Patents, because this data comes from the same data you see on Google Patents. So if Google Patents we certainly have earlier than 1976 patents. Those would be OCR data. But that would be a very just interesting quick query to run to see group by date, how many of them have an inventor field, how many are there? Maybe there's a big drop. there's certainly some dates in there, maybe OCR errors where you see weird dates. But yeah, sorry, I don't know that directly off the top of my head, but it's something that is hopefully now easy to figure out. Yeah. There were a couple more slides real quick. I know we got 2 minutes. There's more slides, and the slides I think are linked from the i3 site. But we did have just some slides on how to add your own data. You can upload simply from your local machine, a CSV file right into BigQuery. You can upload it from Google Drive if you have a slightly larger file, I think up to a gig. And if you have bigger than a gig, it has to go through cloud storage to upload it into BigQuery. And then we do have a fancy tool, to be able to link the numbers together. We have both an API endpoint if you're more computer savvy, and you can give it a messy publication number and it will match it up to the docdb number. Or we have a GUI interface that you can click and go through your results one by one. Go down a couple slides maybe. Yeah, there's this GUI interface where you can pick, open up a CSV file in your browser and it will match up the numbers in your browser and show you the matches. Down another one. Yeah, it'll show the matches for the numbers and you can fix up the number there. And then you can download out your result as another CSV file with one additional column added that has this cleaned up number. So this is really nice if you have a list, maybe of 1,000, 5,000 numbers that you want to match up. It probably will crash on a really huge list. But you can download out your result set and then join it up with all the BigQuery data. So that's really what makes this linking the numbers and the fact that all the numbers in BigQuery, the ones that we've uploaded, are normalized to that docdb format. That's what makes it so easy to immediately join the tables together. So we really want to provide the tools for other people that want to upload their tables to do the same matching, to have the same number format, so they can easily take advantage and other people can take advantage of their linked numbers.
Well, yeah, and the last thing, I know we're probably tight on time, but really just wanted to hear, well, we could share a little bit more about other stuff that we have in the hopper, but also just wanted to hear what other folks are working on and what might be useful for us to do, whether it's, creating some tables with some additional summary statistics, pre-aggregating some stuff, showing more kind of machine learning, deep learning integrations. I think would really like to hear things that we could potentially do that maybe would help your all research agendas along, or help make your lives easier in terms of sort of collaboration or research in this space.
A couple of things related to my earlier point. It would be helpful to have some just high-level summary statistics on the coverage of data over time. Some of us here work with historical data, including myself, hence the question. Another suggestion, kind of unrelated, is I recently found out that there is no comprehensive data on products for US firms, and one more or less comprehensive way to try to measure firm product innovations is classifying patents into product versus process patents. So I guess salute you guys on providing the information on similarity between patents. That's really, really, really cool.
Yeah, it's actually a really interesting nugget. So we've just hired somebody whose full-time job is to sort of try to structure the information inside of the patents. If it's classifying it into product versus process, or the actual steps of the method, or pulling out specific details in the patent, such as number ranges or things like that. So that's a good idea. And that's the sort of thing that we could do, and it would end up in that research table every patent would be marked with product versus process. So if you have simple ideas like that, like if there's a certain segment of the patent corpus that you trying to find a way to pick out like that, feel free to send ideas our way. Yeah, Jay put his email in there. Here's mine. Feel free to email us any ideas, and we'll take a look. Yeah.
This is kind of wacky, and I don't know what the obvious way to deal with it is, but I've been thinking about the inaccessibility of design patents, especially since a lot of the information in design patents is included in images. And so I guess, just thinking about how images can be turned into data that then can be queried in this way would be, I think, really interesting and really beneficial in sort of opening up a whole new area of research.
Yeah, so how would you like to, I guess, what would you group by? So you'd group by design patents that look like a phone maybe, or?
Yeah, I mean, I guess they'd be
some visual
by
attributes. Yeah.
product, right?
Product. So we could look at the sort of the goods and service categories. We've always been interested by those. We've never touched them, but try to match up patents with the trademark goods and service scheme. It's especially a lot of the design patents probably mention in their title some sort of product, like mobile phone case or something like that.
Yeah.
Yeah, image embeddings would be also useful. We haven't started on images yet, but we're looking forward to eventually starting on images.
Yeah, and it's not even obvious to me what features you like are the right features to go after in the images. Just like there's a whole lot of data there that's totally inaccessible.
So for normal utility patents, we've linked up each of the figures. We've OCR'd all the figures for utility patents and linked up the callouts to where they exist in the text. So you see it on Google Patents, you hover over the figure number and it'll be highlighted with how it's referenced in the text. So some of that could form the basis of sort of an image representation just based on how it's mentioned in that detailed description of the figure. There's sort of an image-free way of representing images. So yeah, I heard exporting is a huge thing, and probably most of you won't be using BigQuery. They'll be using BigQuery to get data. Because most of your current research workflows are sort of local. So you use, what are you guys using for tools? Stata and that sort of stuff?
Yeah, Stata or R.
So I think R actually probably has a pull from BigQuery function. So you can just do a SQL query and you can pull in as a like R. Jay probably knows a little bit better.
Pretty sure, yeah, I'm pretty sure there is. I think there's equivalent of the exact same stuff we just shared in Python, but reading into our data frames. I can look into that, but I'm almost positive.
Yeah.
But I feel like I will, like you said, will download the data to my computer, and then the idea is here to use your memory and not, the local computer. So I'm trying to think, how can you really convince people to use your product?
Yeah, and I thought, actually, we're not necessarily, or I guess not at all, maybe trying to dissuade folks from doing that. I think
no, I know, but like I think it's really cool, but I'm just, I'm stuck in my own way of doing stuff, and I'm trying to understand myself. How do I move? And
well, it certainly helps to
hard to change,
Yeah, I think one thing just to maybe suggest is, when we take a step back and think about, well, what are the downsides of basically running a query, downloading the results, doing it locally? Are there some benefits for sure? I think what are the downsides is it's kind of tough to share that with people, especially if you make some changes and then some of those CSVs can get big. So something that might be interesting is, you write a query, you get data, you download the CSV, you do a bunch of stuff locally, but you could then still share that code with people. And instead of having to email them like a zipped CSV that may be super big or hard to kind of move over email or clunky, you could just share with them the actual query that you used and then share with them the code, and then they can run that, and basically they can hit BigQuery, pull it down themselves, and be able to replicate what you did. So the data is local, but essentially the logic to generate it can live in a cloud. So that probably, I would imagine, would be helpful, and actually make collaboration a lot easier, as opposed to having one file that moves and maybe picks up some small tweaks here and there, and then has to get shared out and sent out.
Yeah, I think a lot of the time I just share the output table or figure or whatever, and then there's one person that does the data, and
yeah, and then for
everyone else just wants to see the results.
Yeah, for sure. And of course, for reproducibility, it's always easier in a perfect world to have the code, basically fully replicable code to generate the output. I realize that can be a little tricky.
And
Yeah,
right
sure
now, do you have like, where can we see everything like that is available now in terms of tables? Is there just in your, the slides that you shared, or is there like a link? For example, let's say I want to now send the people that I'm working with, just to show them the data that they could work with if they do an account. Is there a link like for like example of table or something?
Yeah, there's example queries. There's also, we added our links to that i3 dataset sheet that's been going around.
Yeah.
So they
Oh,
mentioned
so
at
it's
the
there.
beginning. So there's links in there to just Google Patents public data sets. And then once you click on that, there'll be all the different tables. And there's other data sets in there. The Pat site group, they put their data sets in BigQuery. And there's a couple other, like Lee Fleming put his data sets in a bit ago, on first term occurrence. But that's why I was excited to maybe join the other group to see how we could help make some of this data more accessible, or at least the metadata about the schemas, not just the table names, but the schemas, example rows, what links to what, things like that.
Cool, thanks.
Yeah. All right, great. We'll maybe rejoin the main group. But feel free to send emails if you have tech questions, if you get stuck, if somebody in your group thinks it's cool and wants a little walkthrough. Happy to chat.